Right, let's go back here. So where would you take the pivot, Ariane? Where would you take the pivot? Pivot at? Oh, you're doing school, so you're the question there. Huh? Pivot at R. Right? So very good. Pivot at R. So what does that mean? He will turn clockwise or anti-clockwise? Clockwise. Right? And what's the perpendicular distance of P from R? Right? Because they give you the values, right? Now it's 6 to something. We have to memorize that. We have to memorize that. It's in school. Right? P by 6, right? And the 200 will turn clockwise or anti-clockwise? So it'll be 200 by how far is 200 from the point here? Right, very good, 1.5. Because it's halfway, right? Huh? Oh, it's halfway. The center of gravity. Center of gravity will act for uniform plan. Oh, sorry, Adam. Adam, many waiting on that. Or let's say Adam, many waiting. Adam, let's say. Right, so yes, 200 by 1.5. So P is how much? P is what? 306, which is 50 meters. That's okay? Sorry, 15 newtons, sorry. It's a force. Right, Kumar? Why say yes? Right, it's newtons. And last part. Who? Nalini? Yeah. Nalini. Wait. First Nalia. Oh, okay, Nalini. Steve. They want the magnitude and direction of the resultant of R and F. We know F and we know R. Get someone else clean it up, right? Hey. Let's copy down P faster. Then give it a tool. Right, so our diagram looks like this. This is 50 newtons. R was how much again? 200. And F is how much? 50. Why? Because anti-clockwise. No, because the body in equilibrium. So mutually perpendicular forces are equal. Okay, our body equal to downward, left equal to right. Right. Pause action again. Right. Nalini, they want the resultant of R and F. So R is acting, F is acting this way, R is acting this way. Where is the resultant? In the middle, a little more specific. Along the flank, diagonal left. Okay. So here is 50 and here is 200. How we going to find the resultant force? Yeah, we did it last lap. Very good. Huh? How are we doing, Nadia? Linear decimal. Right, use Pythagoras, right? So that'll be the square root of 200 squared plus. How are we showing them direction? The opposite direction. Huh? Right, find the angle here. Right, find the angle to the ground. Okay? So yeah, you have to find alpha here. Tan inverse 250. Right, anybody still not in the group? Physics, yeah. Right, Maro, you know. Make us swear some more in that group. Anybody online not in the group?
Yes, sir. I know in the group.
Right, just send my WhatsApp, please.
All right, sir.
Making a month up there, right? 7230529. Right, just to my hands again, please. Adam not in the group. Who else not in the group? Nikolai was the last one again. How you spell Nikolai? Yours is like the switch here with the yes. Well, I think no, let's see. I should have Nalia. It's Nalia and Nalia. Okay, I will save it. Ranju interview? Ranju in group already? Ariane in the group in a hand for. Alright, what's up now? Do you think I've got the numbers? No, I would not have the numbers saved. Huh? I will not have saved now. Take a message.
No, it's me. Oh, me too. I was totally see.
Wait, you come to the wrong class. Very good. Right, here on, what's the last one? Oh, yeah. We got chapter here, right? Should be. I have the beach already. I don't have enough. TV shop, right? Ishmael, I have your name, see, but in Adias, yeah. I guess 50 or 70, but yeah. So you know, How you spell it, Nebula?
I don't care.
Right, anybody miss it? Right, sorry, no finish that question already, right? Where are the pair for?
50 root 7, 89.7 degrees.
And 89.7 degrees? 89? That's the angle? Oh, that's almost 90.
No, and that's kind of
Panel verse 250. Huh? Yeah. No, I did. So mathematics one more time. I tried to start you the. Oh wait, no. Stop, I'll take it out. All right, so now that we all have that, I just sharing back the So where would you take the pivot, Marian? Where would you take the pivot? Girl, I didn't add you. Joel, no, are you ready? Check and see. All right, let's go. Ismail Noah Priya.
I don't know if someone after you. Yeah. I asked about, so, but I think right, you know, I still get my friend.
All right, so let's start, right? So last time we looked at quantities, then we looked at forces and resolving Shivishi. We looked at resolving and forces, and we looked at conditions for equilibrium, right? Now I want to take a look at uncertainty and do some error calculations and things, right? Right, you should have a little note to read out on forces and things, right? I could always give it a trick to read out. I think it is figure out. That's a nice to figure out. That's somewhere it should be happening.
So I know it's easier, but if I couldn't bring questions.
Well, it's like that's like a unit one or unit one question. We'll do plenty. Right. So errors, you may remember errors from form 4, form 5. You have two types of errors, right? Right, random and systematic. Yeah, we just talked about like what random and systematic and how to reduce them. So you remember how to reduce random errors?
Yeah.
Right, just do multiple times on. Get the answer. A systematic error is due to who? Most times in the environment or the apparatus, right? So how do you fix systematic errors? Huh? Well, you can change the apparatus, or you can account for the error by using another formula. All right. So there are two types of errors, which occur in the measurement of a physical quantity: a random error and a systematic error. Right. Random errors, when repeated, measurements of the same quantity give rise to different values. A random error occurs. Okay. So what would be a small random error? In terms of definition, what will be small random error? So you all may have done this, right? You have a little target. Right. So you have a little target, right? And then when you do the experiment, all your values right here.
It's precise.
Right? No, we're not doing precision as yet. But is that small or large random error? Small random error, because although it's wrong, although it's far from the actual value, all your values close together, right? So what it's saying here is that a random error is when repeated measurements give rise to different values. So if you do an experiment and you get a value here, then here, then here, then here, and then Shivish do this value come right here, right? Then you know you have large random errors. Okay. If you do the experiment and all the values close together, it means you have small random error, but probably large systematic errors, right? That's why it's so far away. Right, so a random error is said to be good. This results in a scatter of readings about a mean value, and they have equal chance of being positive or negative. So for example, if this is the actual value, right? When you perform a random error, you can get error here or here on either side. So it can be smaller or it can be larger. Okay. Random errors may be caused by the inability of the observer to repeat a procedure exactly, right? And I give you an example there: variation in reaction time in starting and stopping a watch. Example 2, the interpretation of the actual position of the pointer on a scale. Okay. B, sensitivity of the measuring instrument. For example, the mechanics of the moving coil meter may cause the pointer to settle in different points. Okay. So all these are examples. C, particular measurement not being reproducible. For example, when measuring how temperature falls for times of a particular substance, a value missed cannot be retrieved even though the experiment is repeated. Right? So you wouldn't be able to get that exact reading. Random errors may be revealed by repeating observation of a particular quantity. If an average is then calculated for the measurement, the random error is reduced. Right? So make sure you remember how to reduce a random error. Right? Repeat it and find the average. That's okay. Systematic errors. A systematic error changes all the measurements of a particular quantity equally. Systematic errors result in all the readings being faulty in one direction. Systematic errors may be caused by one, a zero error. For example, a disconnected ammeter reading at 0.2. So instead of it starting at 0, it starts way down here at 0.2. Right? It will result in measurements that are 0.2 too large. Okay? How is cater for that, Shirish? Shirish, how do you account for this error? What you'll do? We have a zero error. What do you do if the value is at 0.2 too large?
You know, like I don't think it's much. So if you put on the other thing, so
So that's minus 0.2, right? Next example, a micrometer screw gauge, which is not at 0 when it's fully closed. You remember that? The micrometer screw gauge, the parallel and that one somewhere here. I was very sure. Anyway, I'll look right. Right, incorrect calibration of an instrument and so on, right? A liquid and gas thermometer which doesn't have 100 equal readings, right? Systematic errors may be eliminated by, or corrected by varying all the conditions in the experiment. For example, changing to a different meter or use a suitable mathematical formula. All right. So now that we know about systematic and random, we have to be able to use the word precise and accuracy properly. So an accurate experiment has a small random error. Sorry, small systematic error. So for example, if you want your experiment to be accurate, where do you have to be? Right, close to the actual value, right? If you want it to be precise, all the values just have to be close together. Okay. So an accurate experiment is one in which the systematic error is relatively small. Precise is one in which the random error is relatively small, right? A diagram is in here.
I was like, I was like, writing this. That gives a life.
All right, so watch here. Here we have a distribution, right? So we did a whole set of we obtained a whole set of values here. Right? We have a whole set of values here. And the measured value is close to the actual value. Right? The measured value is the dotted line. Right, that's like the average value, right? The average value is close to the actual value. So in a case like that, right? In a case like that, what you will say? The measured value or the average value is close to the actual value. Is that correct? And because you have a large scatter of values, all the way here values, right? Because you have a large scatter of values, the experiment is what? Not precise. Okay? Right? How we going? Could you all draw this one for me here? Could you all catch up to me? The measured value is far from the actual value, large systematic error, so it's not accurate, but there's a small scatter of value. So therefore, it's a small random error. Can you use this example here to draw this example? Right in your notebook here. Familiar? Understand? That's it, you ready now?
Absolutely right. That's right.
So this one will be like.
Never. Varatma.
I didn't. It was not snap on call on. But you know, let's say no, she would have you got. I don't know what he is. Yeah.
Right? Well, guys?
I don't know, sir. I have no idea.
What can I accept all, yeah?
Well, yeah. That's
All right, so it looks something like that. Right, Shivish, what yours look like? No, but remember it has to have a small scatter.
I didn't do that. Wait. I do it a measure by its. Okay, well,
Right? It's supposed to have a small scatter, right? Or show you all the wrong thing. No, it just said this one here, right? A small scatter of values and a large systematic error. Right? So it will look something like this, right?
Yeah, I do measure by this one.
Right? So it will be small scatter. Measured actual value there and measured value here. Okay? So the scatter has to be a little smaller, right? I'll be more like that. Right? All the values close together. All right? Online, are you okay with that? Large scatter is like that. All the values far apart. Small scatter, the values close together. Right? Shania?
Yes, sir.
Are you ready? Right. Now let's start taking a look at our calculations now, right? Yeah. Right. So now let's take a look at the calculations, guys. You're looking at precision and accuracy. How to separate them and things and do. Okay with that? Should be well precise. So small one. What type of error is smaller? Small random error or small systematic error? Random.
It's not random.
Precise.
Oh, yeah, it's it was like.
All right. All right. Next is uncertainty. Right. So remember we talked about a little while ago. We talked about if this is the actual value, we could either be positively wrong or negatively wrong. Right? So if the value 10, we could be much higher than the value or much lower than the value. Right? So what we have is, see how far away we are here? That is called the uncertainty. Okay? So the uncertainty is E. All right, so every value has an uncertainty, and we're going to use those uncertainties now in our calculations. Right? E is called the absolute uncertainty. If I were to ask you to find the fractional uncertainty, it will be E over X. If I ask you to find the percentage, it will be the error on X by 100. Okay? Right? Here we have a couple of examples of how to do some calculation with uncertainty. Yeah, okay, we're going to do examples like that. So let us say, I think I gave it out a little while ago, right? Hold on. Let's say I have these quantities, right? Let's say I have A, which is small a plus B uncertainty. And we have B, which is small b plus or minus its uncertainty. Right? What is, and we have S, and S is A plus B. How do we actually find this term? Add up small a and small b. That's okay. How do we get the error in S? Well, we add the error in A to the error in B. That's okay. When it's subtracted now, you do the same thing. Small a minus small b. But to get the error in B, do you minus the errors? No. Why? Why do you ever minus the errors? Because No, why no minus? Because you're decreasing the error. So imagine every time you use an apparatus with errors, it's supposed to increase the amount of errors in your experiment, right? So if you end up minusing, you will be decreasing. So if you use two quantities here, A and B, let's say you use a ruler and a Boolean caliper, and you have to minus them to get the actual reading, right? You have to minus to get the actual reading. Then, if you were to minus the errors, what you're saying is, if I use a ruler and a Boolean caliper, I just got more accurate. Is that true? No. You just add more error into the experiment. Okay, so you don't ever minus error, you always add them. Okay? Huh? Yeah, you have to keep adding error. If you use it twice, add it twice. Okay? Right? When you're multiplying, on the other hand, we have a little maths here. Right? You know, I have to learn the proof. I'm going to stress out some of it, but you can look at the proof, right? But basically, to find the error, when you're multiplying quantities, it's to take the quantity and multiply it by the fractional errors. Okay? So let's do a quick example there. Let's do a quick example there. Right? I'll run board this now, right? Right, so what's here? How do we find the error in the area? So, for us to get the error in the area, the general formula is this. The area by the product, right? The area multiplied by, the sum of their fractional errors. Hold on, I'm going to change this down. Right? So you multiply the area, we have to work out the area. Multiply the area by the fraction, by the sum of the fractional errors. Okay with that? So let me show you how we doing that here, right? No, on my basement. No, take it in first. I'll let you all write it down, right? So how are we going to work out the error? First thing, let's find the area. Area is length by breadth. So we're going to say 2 multiplied by 5. That's 10. Right? S against the meters squared, right? Now we want to find the fractional error. So 10 multiplied by the error in L, which is 0.2 over 5, plus the error in W, 0.2 over 2. When you work out this, that will be the error in E. We have all that. Put the calculator up. What's the error in E there? 10 multiplied by that whole thing. 0.14.
Yeah. 1.2.
Would that 0.4 make sense? No. Would it have made sense? No, because the error gets smaller and we use 2 up. Yeah? The error gets smaller. That doesn't happen, right? The error was 0.2 initially. How much you got? 1.4. So therefore, the area, you can write your answer like this. The value you got, plus or minus the error. That's okay? That's how you do the errors. What would have happened? You're right. What would happen if you had W squared? What would I do? Square the error. It means W squared means you have a next W. So you add on an X fractional error. Okay? Copy down. Let's try a few. Any questions online there? Shania? Any questions? No, you're good? All right. Nalia suggest that I do the next one, right? Yeah, I'll send it to you now. You looking good? Right, copy it down. So again, the two main things that we learned is that we don't subtract errors. And to find the fractional error, sorry, to find the error, we multiply the quantity by the sum of the fractional error. Right, remember you are learning to use the exponentially calculation, correct? Because all these bars will be small and right. Make sure you use the fractional error part properly and calculate. EXP or multiply by 10 to the power. That's also, oh yeah. Right, so in general, I would like you to remember this. Right? Let's say you had something like that. And you wanted to find the error. Right, Aaron? Or you would find the error here. Aaron? And this was what letter had it?
Something. I generally do. Yes.
All right. Yeah. Are we getting the iron P here? Actually, they want to change the slide.
Nothing lasts as long as time.
Yeah, we get again at last. Right. What's the general thing here now? What's the general way, Divish? What's the general way to get the errors here now? Yeah, here on. Right, it's always P by the fractional error for all of them, right? What's the fractional error of Q? 10 to the power n. Delta Q on Q multiplied by n. What does Q3n mean? It means Q by Q by Q by Q by Q until n, right? Correct?
Yeah.
So you just simply adding up all of that. So instead of adding up all, just put n in front of the fractional. So in short, if you see a power, if if you see a power, right, just multiply the fractional error by that. What's the next one? What's the next one? It's delta R on R by. No, that's no good. That's small q. And let's shoot card like plus what? So Ryan, what's the last part? Multiply by s, right? So this is the general form for error. Multiply p by the fractional error by the power. Next up, you fill up form. Full form. Anybody else doing physics fill up form? Anybody else doing physics with this tool? That's cool. Listen. Ready? Right, so that's the general way to work this out, right? All right, let's try this one here now. All right, so let's try this one here. Right, sorry to give you so much quantity in the first one, but yeah, we have all right. Hold on, a little bit short. Now,
Yeah.
all right. All right, so we have to find the uncertainty E there. So the first thing I want you to do is to write down the formula for the uncertainty E. Right? Please remember that 4 and 5 are what? Constant, right? So they have no error. Go ahead. Write the error E there. Come on. Use the general and let's give you. Write the formula, write the quantity, then work it out. One of the things I want to learn when you're doing these things is that you must work in a cycle. Okay? So convert the millimeters to right? Try that fast. Let's see if we can do a few. Just have to think about yeah, this one. Right, there's a chance next week might not have any class, right? Oh yeah. For sure next week is not safe. Oh, I might have a class on that, you know.
So that's it.
Yeah, developing. Yeah.
Next week.
Sign up.
We're going to stay till
Yeah. So we don't know how many. That's a big year. We want to say. Yeah. What else? If you have until like 10.
we will have the 9.
No, 10.
It's been 9 to 2 weeks. It's always. You wanna have.
Yeah, we can do that.
We'll see. We'll see.
We can check.
Yeah, I think what was.
What about you? Huh? Yeah. Yeah, that's it. One is mass. Look at it. Mass, length, gravity. T is extension and T is diameter.
So it's all right, I think that's it.
Yeah, write it down, but I want you to, no, you don't write it down, just take notes. Let us work it out. I want to do something on the board, right? Those who are online, just look at the camera. Right, look at the camera and I'll be writing the answer on the board. All right, so let's see if we get it. Let's see if we get it right now. That's not how I do that. That's 2 minutes. We should have 4, all right. And plug in the device and right, online, make a look at the camera, right? Shania, you see the camera, and you will see me on the whiteboard. Ishmael, you'll see me, right? You'll see me, right? Yeah, you'll see him, Ishmael. You see enough?
Yes, sir.
Okay, I want to make sure. Right, so help me out here, please. Aria. Right, arrow M on M. Right, arrow L on L. So we done with those two. Next one is what? Delta. Nice. Right, always division is still added. Right, every quantity contributes errors. Okay. Plus arrow in E on E plus on D, right? The reason for the 2 is because it's this squared. Right? And then plug in the values, right? But before you plug in the values, you have to find E first, right? Go ahead.
Actually, because they are. No, that's very subtle.
It will be an error, but it could be an out. Oh, yeah, you have to say you don't understand. Do it that way. That's not much more than it's.
That's no, I don't think they never had. I never did. Europe. I said
That's how she feels. Yeah. I could live with it. Yeah. It's after when I'm good.
Yeah, everything. Just get any habit using the right unit. So number one, let's work out E. So that's 4 by the mass. The mass is 5. The length is what? The length is 3.025. Gravity is 9.81. And you divide it by pi by the error. Sorry, the extension 1.27 working SI units. That's 10 to the minus 3 by d squared. 0.84 by 10 to the minus 3. Right, and then don't forget to square it. So how much is that? How much is that for E? Make sure you have the SI units here. 10 to the minus 3, right? Correct value. So we should not working it out. Stamina. What point? Yeah. Yeah, I don't have this as yet. So I'm working out this first. Remember, I need this. So I worked out that here. I need E. So I work out E first, and then I'm going to try to work out this. Yeah. So you need a quantity for E. You need E. And then E by the sum of the fractional errors. That'll give you the error in E. 2.11 by 10 to the 11. All right. Yeah, so you need to get this right. So you're putting all that. Yeah, triangle. Yeah, kind of.
Yeah.
Yes. This one a triangle is. Right, and now you're gonna plug everything in. So it will be 2 point. Anybody else got 2.11 by 10 to the 11? Huh? How much y'all got? 10 to the 11? Okay. And then you work it out here. The error in the mass is 0.002. Error in the mass is 0.002 over 5. Error in L is 0.005 over 3.025. And the error in G is 0.01 over 9.81. Error in E, what you say earlier? Do I necessarily have to write for the error part? 10 to the minus 3 here and 10 to the minus 3 here? No, because they'll cancel out, right? But as a habit, you can still write it, right? You can still write it as a habit, right? But you don't have to, right? And last part is 2 by the error in D on D. So that is error in D is 0.8, sorry. 0.01 over 0.84. How much you get it? Huh? Yeah, no. What I was saying, it'll cancel out. So you don't necessarily have to write it in the fractional. Okay? Work out that some of what you get. Yeah, I think that's 10 to 9. Take it and see again. Oh, here. Huh? Because some more, it had to be less than 2.11. Huh? 10 to the 9, 8.99. Anybody else got that online?
Yeah.
8.99 by 10 to the 9.
Yeah. So it's 99.
What mean? Right. But she got the same thing as when you do. Let's check it back and see if they put something wrong. Any multiply by 2? Anybody else got 8.99 by 10 to the 9?
Yeah.
Yeah? Kieran got 8.99 by 10 to the 9. Anybody else online got that? Adam? What you got, Adam?
Sir, 0.22.
Okay, go ahead. Right, we still have to write the final answer. So we had to find a way to put them together, right? Come on, ready?
Yeah.
But this was a little less fun. This one I'll show you that's not a little less fun. Right? So watch this here. How do we put them together? We have to make sure that they both to the same units. Right? So you can put them both to 10 to 11 or 10 to the 9. Okay? It will look nicer if both of them are 10 to the 9. So if I move it to decimal place twice, you'll get 211 by 10 to the 9. That's okay?
Yeah.
So if I bring these two together now, the final answer is 211 plus and minus 8.99 by 10 to the 9 Pascal. Yeah, well, I'll teach it later. The jump modular. I think he was jump modular. Yeah. Huh? He is jump modular. You jump per meter square is down. Right? So again, remember that we need to do two things. We need to find E and then the fractional error. Okay? And the handout of a little space where to fill those things out, right? So I did it by 10 to the 9, or you can do it by 10 to the 11. Up to you. Next one, let's go again. Let's go a little faster this time. Less quantities here. Any questions online? Joel? Safir, or again, Shida? Right, let's go again. Or is it US one? I'm still gonna wait if you do it, right? Actually, come on, go. Oh, yeah. Oh my God, one side. Right? G gravity, where you recognize the problem that. And it'll give you a GL subject formula. Right? You all might do this now. Right? They wanted to find G and the uncertainty, but I gave you T as the subject formula. So what you have to do? Rearrange and make G the subject, and then find the error. Okay? Go ahead. The other rearrange it and make G. The root is not sure what to do, square both sides and then. Right? Yeah. Go by where? Oh, because
I didn't even understand. I didn't even understand.
Right, so the first thing I do is to make G the subject, right? Let's just make sure you do that properly. I just give you a few hints there. Right, again, those who are online, you'll see me on the whiteboard doing distribution on the whiteboard, right? Nobody not. Oh, yeah, yes. All right, so first thing, we have T is equal to 2 pi by the square root of L on G. So if we square both sides, we'll end up with T squared is equal to 4 pi squared by L on G. Right? Carry across 4 T squared. So you'll get T squared is equal to 4 pi squared is equal to L on G. I want to make G the subject. I just going to cross multiply. So I'll get GT squared is L 4 pi squared on, sorry. This by this is this by this is that. So G is equal to L 4 pi squared all over T squared. You get that? I did crazy looking. Okay.
I just clear my.
Huh?
Yeah, I mean. So I don't know why you had it so like scientific.
So why had to carry 4 pi on this side?
Yeah, can I, it's just square.
All right, yeah, I get this guy. It's up to you. Right, so you square both sides, the carry across the 4 pi squared, you have two fractions cross multiply.
9.7.
Once you get the same thing, yeah, that's a good sign. Right, so first thing first, work out G. G is the length of the correct SI unit. Right? By 4 pi squared all over T squared, so that is 2.16 squared. What you got for G? 9.73. Yeah. Now you want to get the error in G. Can I get the formula there? What's the error in G? Yeah. Go ahead. What's the error in G?
Change in L.
The error in L on L plus
Change in G. Change in 2G.
You sure? 2 by the error in T on T. Watch this here. Remember, you want to get the error in G. So the only two quantities that are affecting G is L and T. Right? Oh. So the error in T on T by 2 of that. Why 2, Shamish? Right? Because of this squared. Good. So this is 9.73 by, what's the error in L again? 0.005 all over 1.15 plus 2 by 0.01 over. Remember, if you do this and you get a value bigger than G, something wrong, right?
0.13.
Anybody else get up? 0.13? Yeah, 0.13. And then combine your answers. 9.73 plus or minus 0.13. Okay. So that's the way you work out your errors. And there is one more you can do here for homework. Yeah, look at it. Two you can do for homework, right? 2008, 2003. All right, copy it out. Next day we'll continue with that. Again, no face-to-face next week for sure. Message about online, right? Huh? Yes, we'll read some definitions and things online. Excuse me, you didn't write it down?
I didn't have to write.